This is a really popular style of question in the FRCA primary because it tests a lot of different parameters of your pharmacology. So, a posh new volatile anesthetic agent has the following properties. It has a blood gas partition coefficient of 0.14, an oil gas of 1.9, a MAC of 71%, a boiling point of minus 108 degrees Celsius, and it is less than 0.00001% metabolized. So which of the following is true? Is it more hepatotoxic than halothane, more potent than isoflurane, slower offset than sevoflurane, less volatile than desflurane, or is it faster onset than nitrous oxide? So you need to know each of these parameters for each of the different agents to be able to derive the answer. And therefore it's a very effective question for testing lots of pharmacological knowledge at once. So we'll quickly go through it. We'll start with hepatotoxicity. So hepatotoxicity is going to depend on many factors, but it's largely correlated with how much metabolism the drug undergoes. So if you undergo very little metabolism, that means you're breathing it in, it's going around your body, going to the brain, going back into the blood, and then you're breathing it back out again. And so the less metabolized something is, the less toxic it is because you're producing fewer breakdown products. So this requires you to know that halothane is 20% metabolized, sevoflurane is 2% metabolized, and our new agent is less than 0.00001%, which means it is going to be vastly less hepatotoxic than halothane. So this answer is wrong. More potent than isoflurane. So potency is related to the oil gas partition coefficient. When we give our volatile agent to our patient, we give it through the lungs, it diffuses into the blood and then to the brain, which is mostly fat. So if something has a high oil gas partition coefficient, this means it has a very high affinity for diffusing into fat or oil. So the more keen our agent is to get into oil, the more keen it is to get into our brain, and therefore the less we need to give in order to get a clinical effect. So if something has a high oil gas partition coefficient, it is more potent, and therefore the minimum alveolar concentration needed for it to be effective is lower. We've done other videos on MAC, and we won't go into the whole thing here, but basically MAC and oil gas partition coefficient are inversely related. MAC is the how much do I need of this for my patient to be adequately asleep, and oil gas is how much does this drug like dissolving into fat. And it requires you to know the following data points. Isoflurane has an oil gas of 91, so it is 91 times more keen to be in fat than it is in gas, and therefore it has a MAC requirement of 1.2%. Sevoflurane is 47, is about half as potent, so you need to give about double, 2.1%. Desflurane is 19, so you need to give a lot more, 6.6%. And our new agent is only 1.9, meaning it's not very potent at all, and you need a MAC of 71%. This means, well, the gas mixture the patient is exhaling needs to be 71% new agent for that patient to be adequately asleep. So it's really not very potent at all. So we can say it is definitely less potent than isoflurane. So this answer here is wrong as well. Speed of offset and onset we'll do in a minute, because we can do these two together. Volatility is almost entirely to do with boiling point. So if something has a low boiling point, that means it is more volatile, because volatility is a measure of how keen something is to evaporate. And if it has a lower boiling point, it means that at any given temperature, like room temperature, it's going to be more keen to evaporate than something that has a much higher boiling point. So desflurane has a boiling point of 24 degrees Celsius, which means it is pretty much boiling off at room temperature. But our new agent has a boiling point of minus 108, which means it has boiled off long before we reached room temperature. So it is definitely more volatile than desflurane. So this answer is wrong. We'll do these two together because slower offset and faster onset are the same parameter, and that is blood gas partition coefficient. This is the least intuitive parameter and takes a little bit more explaining. We're going to go back to our little diagram. We're going to give our inhaled anesthetic. It's going to go into the lungs, then into the blood, then into the brain. Blood gas partition coefficient is similar to our oil gas, but instead of measuring how keen it is to dissolve in oil or fat, it's how keen is this agent to dissolve in the blood. Now, if we have a high blood gas partition coefficient, this means the drug is very keen to dissolve in the blood. which means if we give it to our patient, it's rapidly going to move from the alveolus into the blood, and then it's going to stay there quite happily. And it's not really going to come out of the blood into the brain because it doesn't want to. So this means we kind of have to saturate the blood with agent so that it fills up, and then the drug starts to move into the brain. So we have to give agent for longer, fill up the blood, and then it will diffuse into the brain and start having a clinical onset. Likewise, when we stop giving the agent, the patient's blood is full of the agent that we're giving, and the brain is full of it too. It's going to take much longer for it to diffuse out of the blood into the lungs to generate a concentration gradient from the brain to the blood for it to start then diffusing back out of the brain. So all of this is to say, if you have a high blood solubility or a high blood gas partition coefficient, everything happens more slowly because you have to fill up or empty the enormous reserves of agent stored in the blood before anything significant will happen. So if an agent has a smaller blood gas partition coefficient, so it is less soluble in blood, everything happens faster, the onset and the offset. So sevoflurane has a blood gas partition coefficient of 0.65, nitrous 0.46, new agent 0.14. So the new agent is much lower than the other two, so it's going to do everything much faster than the other two. So it's going to be faster offset than sevoflurane, and it's going to be faster onset than nitrous, which makes this final option the correct answer. This agent is faster in onset than nitrous oxide, and it is because the blood gas partition coefficient is much lower than the blood gas partition coefficient of nitrous. That is why this kind of question is so popular in the FRCA, because it tests all of this knowledge, and you do need to know these individual numbers for these agents. You will just have to do that as a memorization exercise, and eventually you'll have done it so many times it just becomes routine. But you do need all of that knowledge to be able to answer this question.